Yeah. Okay, so I am going to talk about spectral form factor in fermionic and bosonic models of many-body quantum chaos. Let me begin by reading the abstract which I have proposed to tell you. So I will discuss quantum chaos and spectral correlation in periodically driven fermionic and bosonic interacting chains in the presence and absence of total particle number conservation. I will show that the spectral form factor precisely follows the prediction of random matrix theory in the regime of long chains and for time scale which is beyond this Thouless time. For long range interaction, I will use random phase approximation to calculate the spectral form factor in terms of a bistochastic many-body process which I will generate through some mapped Hamiltonian of spin and bosons. Particularly for spin will be for fermions and boson for bosonic system, the mapped Hamiltonian will be bosonic. And then I will show in the particle number conserving case, the spin Hamiltonian has SU2 symmetry and the bosonic Hamiltonian has SU11 symmetry. And those symmetries will help me to find the scaling of Thouless time with system size, which will be in these cases quadratic with system size. And then I will show that in the absence of particle number conservation, while the kicked fermion chains, Thouless time is independent of system size, for the bosonic model, there is system size dependence for the Thouless time, beyond which this random matrix description appears. Okay, so the model which I consider is a 1D lattice of interacting spinless fermions or bosons, with time periodic kicking in the nearest neighbor coupling. So this is the Hamiltonian which has two parts. The H0 part has random on-site energies and long-range interaction between two particles. And then I have kicked part of the Hamiltonian which is this term which has hopping with J strength and pairing of two particles, either bosons or fermions, with delta strength. And this kicking is happening at some integer time m. Okay, so in this model or this Hamiltonian, if delta is absent, so then the total system is particle number conserving, and if in the presence of delta, the total particle number conservation is broken. So I will use absence or presence of delta to get the model with U1 symmetry or without U1 symmetry. Spectral form factor is a good quantity to describe quantum chaos. So fluctuation and I will try to describe to you what is spectral form factor I am using here. So what I am interested for spectral density, in calculation of spectral density as well as fluctuation in spectral density, or whose Fourier transform will be spectral form factor. So the energy which I am interested for this kind of time periodic model is the quasi-energy of this quantity U, which is U is Fouquet propagator for one time evolution. So this model which I have like kicking at unit time, so U is time evolution under one evolution, means first evolution with H0, which is and then one kicked. So U is that propagator, and the quantity which I am interested is the eigenphase phi m of that U. So I can define a spectral density of this phi, and then also I can define the fluctuation in spectral density, and this is this pair correlation function, which is 2-point correlation of spectral density. And then if I take Fourier transform of this pair correlation function, that is what I call spectral form factor for our study here. And one can show that this will be written in this form, which is trace of U of t, this U, and multiplied with trace of U of minus t, expectation over average of this disorder, which I have chosen from a Gaussian distribution. And I will try to show you how I calculate that quantity. So now this U, which I have written here, So I can break it as a two-step Fluke operator of W and V. W contains the H0 part and V contains H1 part. Yeah, one can do numerically, but the full calculation I'm going to show analytical. So it's difficult to calculate M directly. So I will not be able to calculate M directly, the eigen and phi M eigenphases. So to do analytics, what I will start with, I will start a basis which is eigenbasis of W. So I choose Fock state basis, and here N1, N2, NL represents occupation. So that is where we have difference between fermions and boson. So fermion occupation will be 0 or 1, and bosons can be 0 to N, where N is the total number of bosons in the full system. So now I will not go through all the long calculation how I calculate spectral form factor, but I do two approximations for this calculation. So I use a random phase approximation for performing disorder average over those point disorder, and then I will do another approximation to make an identity permutation between two replicas in time. So this forward and backward in time. So I will use an identity permutation between replicas to show that the spectral form factor can be written as 2T trace of M of T. This M I will show that is a Markov matrix. So it's a bistochastic matrix because its elements along row or column is total 1. And this M matrix, which gives the process how chaos is reached in these systems, and I will try to explain that. So is given by expectation of exponential of IH1, the kick Hamiltonian mod square. So now my purpose is to try to understand the properties of this Markov matrix for bosonic and fermionic models and try to predict about Thouless time. So before I do that, one thing about Markov matrices that it has largest eigenvalue 1 because of this double stochastic property, and because my matrix is also real and symmetric, all the eigenvalues are also real. So I will then can arrange these eigenvalues as 1, lambda 2, this order, and then I can write the spectral form factor due to this trace of MT as 2T1 plus sum over J lambda JT. Now, in the leading order, this has, because all the lambdas, as I said, the largest eigenvalue is 1 and all others are smaller than 1. In fact, this is what I have shown in as a direct calculation of M matrix eigenvalues. So they are smaller than 1. So I can say that leading order behavior for this system, I have spectral form factor 2T, which is also what is predicted from random matrix theory for this kind of system, which is circular orthogonal ensemble. So because we have a time reversal symmetry in this model, so we have a circular orthogonal ensemble, and the leading order behavior here will be 2T. So one thing which actually I forgot to say, one of the motivation of doing all this calculation, that to understand why random matrix theory is so successful in giving spectral form factor for say. So in our this time evolution calculation, we could show that the mechanism through this M matrix, which I will discuss more, that how random matrix theory behavior appears. So next I will try to calculate the properties of lambdas. So for that, what I will do first, I will first try to say that I am interested in a time scale which is longer than 1, let's take, and which is shorter than the Heisenberg time when system saturate. So in that time scale, we can mostly discuss all the phenomena using lambda 1 itself, leading eigenvalue. And if we say that lambda 1 scales as with system size something like 1 minus 1 by T star, where T star I define as Thouless time, and I define T star to be L to the power beta by D, and I am interested in calculating beta. So if I kind of do this means approximation of truncating the system in lambda 1, so I get 2T 1 plus lambda 1 to the power T, which using this form I can write 2T 1 plus exponential of T, exponential minus T by T star. So the 2t will become when t is longer than t star, and that is where the universal RMT form appears. So now t star I will try to calculate, and I will do it in two ways. One is I can do direct numerical diagonalization of M matrix, but also I can calculate the M matrix, Markov matrix directly, and that is what I will show you here. So I calculate Markov matrix in the total regime, small j, small delta limit. First, I am trying to show it Fermion's case, and in the Fermion's case, that matrix looks like, means the mapping looks like anisotropic Heisenberg model. So this is Heisenberg model, and it has the coefficients are anisotropic, and in this case, when you can see delta is 0, then it's isotopic model. Isotopic Heisenberg model has SU2 symmetry. So because of SU2 symmetry, for any magnetization or any n, the behavior will be same for the Thouless time, and one can calculate because of the properties of Heisenberg model, the T star here, Thouless time, depends on L squared, so beta is 2. So with growing system size, your Thouless time increases for reaching universal RMT form. In the case of delta non-zero case, in absence of UN symmetry, there is again using anisotropic Heisenberg eigenvalues, we can show that beta is 0, so Thouless time is independent of system size for the Fermionic model. And same thing we can do for Bosonic model, and in that case, what I will show that this is the mapped model, is not known model, it's a little bit unknown, means it's a bit unknown, and still one can study the properties of this model, and what we will do, means what I can show you that this model has SU11 symmetry. So it's also some kind of like symmetry like SU2 with finite Hilbert space, but this is for infinite Hilbert space for bosons. And using SU11 symmetry of this model, one can say that again for different particle number sector, you have same eigenspectra property of this M matrix. So that means I can use single boson sector to calculate lambda 1 L dependence. And in this case, again particle number conserved case is L square. So quadratic system size dependence both for fermions and bosons with UN symmetry. In the absence of UN symmetry, I said that for the fermions, it's independent of system size, but for boson, it depends on system size. So Thouless time again increases with system size. It is T star equal to L to the power gamma, which is around 0.7 plus minus 1. And all these things which I have told you that using RPA, random phase approximation, and identity permutation, all these things, and I can show you that if I can do a exact numerical computation of KT, so our prediction actually, like this quadratic scaling of Thouless time actually comes up, which I showed here. And that's all. Thank you. So this is the two references. The first fermions one appear here, and second one here. So both the works are done with Professor Thomas Prosen from Ljubljana, and this person Divij Mishra, he is a student in IISc, Indian Institute of Science. All right, thank you.
So the RPA and the identity permutation, the identity permutation that you did, is that actually equivalent to doing what is called the diagonal approximation for the Feynman histories of the operator? So, if I can write u to the power t as some path integral, right? And then I'll have some forward going paths and I have some backward coming paths for the u to the power.
So what identity permutation means, like within this time window of the replicas, all the like this Fock space occupations are repeating in the.
Basically, the paths do get paired.
Yeah. So, so I can choose a cyclic and anticyclic permutation of these occupations in going forward, and that will be repeated in coming backward.
So it is really the sort of pairing of the Feynman history.
Maybe
because this is the sort of people who did.
Yeah, that's what probably this Oxford person.
Actually, even before this, people used to do this for the semi-classical random matrix chaos.
So random matrix theory? No, so this is everything I'm calculating in time domain, right? So I'm not doing, means this is also one goal of doing this. So random matrix theory, you do everything through ensemble average, right? And here we are doing mostly temporal calculations. Yeah. So it's that way different. So we are giving one kind of, you can say that justification for success of random matrix theory.
Okay.
What is the random phase approximation in this context?
Yeah, so random phase approximation, what I am doing, this you can say that this phi m I am considering for different this Fock state basis, they are random.
Phi m are just random.
Phi, the eigenphase of the Fluke operator, you can think. The phi m.
Okay.
So those are random over my different realization of the systems when it's growing over time.
Just had one question. So this Thouless time, and can you just remind, like, what does it tell us finally about the like chaos in the system?
Yeah, so what this one is actually borrowed concept from disorder system. So it's like when system losing the coherence kind of, right?
Yeah.
To becoming this universal RMT form.
Equivalently, you can say that when the system begins to mimic random matrices. So there's a time scale before which the system doesn't actually know that it's completely chaotic. So the time scale at which it begins to mimic random matrices.
Dibyendu, and the next.